Okay, now let's move to the description of our CRS-10 cards. And we'll start with the PLIM. The PLIM is the physical layer interface module that will be paired with a MSC or FP card. And on the CRS-3, the PLIM role was to handle the layer 1 and layer 2 tasks. But on the CRS-10, we are moving all the layer 2 activities into the nPower X1E. So the PLIM will basically only do the layer 1 job. The first one here I described will be the 40 by 10 GiG WLO. This card will offer 40 optic slots for SFP+, and it will support LAN-PHY, WAN-PHY, and OTN G709 FEC. So if you remember, we described the concept of slice earlier, and here it will be easy to see the slice because we will have two daughter boards of 20 ports each. So each slice will match one daughter board, and each daughter board will be facing one nPower X1E on the MSC FP or LSP 400 card associated to the PLIM. So this card is available in iOS XR 5.1.1. That was the first version supporting the CRS-10. And as we said before, we will have the WAN-PHY, LAN-PHY support, but also all the OTN G709 and the different flavors of FEC. Depending on the version, we will support different type of SFP+, but in 5.1.1 we will have the SR, LR, ER, and ZR. And it's important to differentiate each type of optic module because depending on the reach you want to have, you will have different type of power. And the card will have different slots for each type of optic power requirement. So we have a total power budget here of 45 watts. That means 30 ports at 1 watt plus 10 ports at 1.5 watts. So the last 10 ports will be dedicated to what we call the high power optics, namely the ER, ZR, or DWDM. That's the one at 1.5 watts or more. If we are exceeding this power budget, the port will not boot. Also, it's important to understand how the card will behave depending on the type of chassis it will be inserted into. On the left, the port numbering on enhanced chassis will be from 0 to 39, from the left upper side to right on bottom side. On the legacy chassis, we have one slice being shut down, and the port numbering will start here at 0 up to 19. And if we take the example of the port 26 on an enhanced chassis, it will be here the port number 6. So this port numbering will appear clearly on the front plate of the card. Also, the code of color here is yellow and purple. Yellow will be for the low power optics, the 1 watt optics, and purple will be for the high power SFP+ modules. Now the second PLIM, the 4-port 100 GiG, that's the one leveraging the new CPAC optics we described. And again, we have two different slices and two different submodules, each one handling 2 ports 100 GiG CPAC. In 5.1.1 we support this card, and we have two types of CPACs that are supported, the SR10 and the LR4. The other type of CPACs, so the ER4 Lite, the 10 by 10 LR, and the breakout options will be supported in future versions. So what we have here is LAN-PHY and OTN OTU4 G709 FEC. Like we described before, the port numbering will depend on the type of chassis the card is inserted into. So the 100 GiG 0/X/02 will be 0/0 on a legacy chassis. Finally, the third PLIM will be the Flex one. That one offers 2 ports 100 GiG and 5 port 40 GiG. and we support this card starting from version iOS XR 5.1.3. So the upper slice will be the 100 GB slice, and the lower slice will be the 40 GB slice. And for this 40 GB, we will support optics of QSFP Plus type. The support also on this optics will be G709, FEC, and LAN5 Wi-Fi. Port numbering, same rules again. We have on the same card, if I take a look at my interfaces, 140 GB, and on the legacy chassis, the slot 0 will be the first 40 GB slot. Now let's move on to the description of the MSC, FP, and LSP 400 cards. These cards are paired with the PLIM we just described, and each one is composed of 2 identical slices. Each slice is composed of 1 nPower X1E ASIC and 2 in-bar FIA ASIC. Let's start describing the nPower X1E. It's an ASIC made based on Cisco design. It's a 40 nanometer ASIC, and we are sharing the same type of architecture than the other one, the nPower X1 used on NCS 6000. For each nPower X1E, we have 336 PPEs, packet processing engine. They are gathered or arranged into clusters of 16 each, and we have 11 clusters assigned for ingress and 10 clusters assigned for egress. The total capability of the ASIC is 230 million packets per second, more or less, and 200 gigabit per second of bandwidth. We are not using local TCAM, we are using an external TCAM in the line card, handling our 80 million entries. And each ASIC will be able to do or to support a total of 9 million IPv4 VPNv4 routes or 4.5 IPv6 or VPNv6 routes. That does not mean that it is the current scalability supported on a CRS-10, because the CRS-10 needs to be backward compatible with the other generation of cards, CRS-1 and CRS-3. We are limiting the usage of this ASIC at 4 million entries today. So the ASIC is also responsible for the queuing, and it will be able to handle a total of 120K queues with 8 different levels of QoS. We are describing now the in-bar or FIA. Again, it's a home design product, and we are aggregating the role of the ingress queue and fabric queue here. We have 2 different modes on the chassis. We will support the 400 GB mode, basically having connection, 16 connections at 8.6 gigabit per second into the fabric. And the second mode we have on this will be the 200 GB mode. In that case, we'll have 32 connections at outer speed 4.3 gigabit per second. If you take a look at the speed or the connection we have on each in-bar, on the upper in-bar we are receiving unidirectional traffic from the nPower X1E ASIC at 276 gigabit per second. And on the right, we have only 138 gigabit per second bidirectional from and to the Sapir ASIC. On the bottom one, we have also one unidirectional connection to the X1E, but only also at this time at 276. So we have some kind of mismatch into the speed. That's why we are using MUX to split the traffic, the incoming traffic or the traffic coming from the X1E into the fabric. It's going to be split between the twin bars to reach the full capability, and vice versa. For the traffic getting back into the system, it will be split into the 2 different in-bars and regathered through the MUX to be sent to the X1E of the line card. So these 2 different modes we described, the 400 GB mode, we will have the 2 slices active at the same time, And we have, for each in-bar, 16 connections at 8.6 gigabit per second. But if we are inserting this same line card into a CRS-10 with a legacy chassis, we will have only 200 gig or one slice active at this moment. And for that, we will use 16 connections at 4.3, so it will be at half the speed but twice the number of connections to the fabric. So, and for that we'll use the CDR described here to spread the load inside the system. Finally, let's describe the fabric card and the Sapir, the fabric ASIC. On the right I have my CRS-3, and on the left my CRS-10. On the CRS-3 right, I did have a total of 6 links at 500 gig in the line card to fabric direction, and I did have twice 4 connections in the direction of fabric back into the line card. So for each fabric queue I used to have 4 connections at 5 gig, and we have 2 fabric queues. Things are a little bit different in the case of the CRS-10. In that case, I will have the same number of links in each direction because they are bidirectional, as we described before. And this time we will have 8 of each at 8.6 gigabit per second. And to conclude this hardware presentation, I will briefly introduce the SCGE22-B card, which is a replacement of the SCGE22. This card is used into your fabric chassis, the FCC, and it's a replacement driven by the requirements of the lead-free legislation. The card now is Intel-based. That means we replaced the PPC model or architecture with x86 architecture, and you can replace them in service. Thank you. Ta 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 ta.